In this video, we're going to go through the properties of logarithmic functions. We have the product rule, the quotient rule, the power rule, and we're going to use this to simplify and expand logarithmic expressions. We're also going to learn the change of base. The first one that we are going to look at is Theorem 6.1. And we know this from our previous section, is that this is the base, this is the exponent, and this is the answer. So we know that we can write this as here's the base, here's the exponent, here is the exponent, and here is the answer. So we know that we can go from logarithmic and exponentials fairly quickly, provided, of course, I have a single logarithmic function equal to a single number. Equivalently, if I have a single exponential equal to a single number. Two new ones that we pick up are the log base b of b to the x is equal to x. Now this makes sense because, remember, this is my base, this is my exponent, and this is my answer. So b raised to the x clearly equals b to the x. Let's take a look at our next one. The next one in 6.3 is b raised to the log base b of x is equal to x. Well, if this is my base and this is my exponent and this is my answer, if I write it in the logarithmic form, then I'm clearly going to get the log based b of x is equal to the log based b of x. And so that makes sense. Now, with our next theorem, 6.4, if we have my b raised to the u, and I have b raised to the w, this only holds true if u and w are the same numbers. This is going to be important later in this chapter. What we also get with this theorem is if I have the log base b of u is equal to the log base b of w, then this only happens also when u equals w. Notice, however, there is a restriction on u and w, and that's because of the domain of logs, and the domains of logs have to be larger than 0. Our first rule of logs is the product rule. The product rule is, I'm going to zoom in on this so you can see it, is notice I have a multiplication going on between m and n. That relates to an addition sign between them when I break them apart with the logarithmic rule. The rule that this corresponds to in exponents is if I have a raised to the m multiplied by a raised to the n, then I have a raised to the m plus n. Notice I am multiplying my bases and I am adding my exponents. That's the same thing I'm doing here. These m and n's, remember, both m and n are exponents. That means I can break them apart with addition. So if I'm asked to simplify these completely by expressing in terms of sums, then I ask myself what is going on between the two between the two factors, and it's multiplication. So I can write this as the log based a of x plus and that's because that's multiplication, so that becomes an addition, of the log base A of y. If we look at b, we have the log base 4. Now remember, this is multiplication of 5 plus the log base 4 of 64. The log base 4 of 5, there's not much we can do with it, but what I know is if I take 4, raise it to the third power, this is equal to 64. So this expression is equivalent to the log base 4 of 5 plus 3, because I can replace the log base 4 of 64 with 3. And we learned that from the section 6.1. My very last one, as an example here, I have multiplication going on between e and y and x. So this will become the natural log of e plus the natural log of y plus the natural log of x. But we know when I have the log base b of b, this equals to 1. Specifically, the ln of e is the log base e of e. So this expression is equivalent to 1 plus the natural log of y plus the natural log of x. Our next one is the quotient rule. The quotient rule is if m and n are being divided, then that equates to a subtraction. Remember, these are exponents. The exponential rule that this belongs to is if I have a over m divided by a over n, because my bases are the same, I can subtract the exponents, which is what I'm doing here. So if they ask me to write this in sums and differences, then I have to determine what's going on between each of the pieces or factors. Between y and x, I have division. So this is going to simplify into the log base a of x minus the log base a of y. And it has to be a minus y because y is in the denominator. Similarly, I have the log base 4 of 5 minus the log base 4 of 64. But from our previous examples, we know that this is going to be equal to the log base 4 of 5 minus 3. Now, this minus 3 is going to be important when we start bringing these back in. I can bring in a number, any number, into the log expression by knowing that the log base 4 of 64 is equal to 3. So if I'm given 3, then I can replace it with a log base 4 of 64 if my base is 4. Looking at our next example in C, I have the natural log of e minus, and I'm going to put this in parentheses, the natural log of yx. But this is equal to the natural log of e minus, now yx has multiplication going on between them, so I can break that up into the natural log of y plus the natural log of x. We know from our previous examples that natural log of e is 1 minus, and you can distribute that negative 1 through, or you can leave it. I'm going to go ahead and distribute it through, so it's a negative log of y and then minus the log of x. For my next rule is the power rule. And the power rule is this exponent, which is onto the m, comes out front as a multiplier. So as you are thinking about what you'd write on your note card, these three rules are perfectly good things, and you probably should consider putting these on your note card. So the correspondence to this is if I would have had a raised to the m raised to the n power, then notice it is a multiplication of those powers. And logarithmic functions are just exponentials. That's all it is. They're just exponents. We've talked about this in our previous section, and we talked about this in our previous section, so these are kind of important. consider writing those down on your note card. So we also have these, which we talked about in the beginning. Log base b of b to the x is x. B raised to the log base b of x is equal to x. If I'm asked to evaluate these without using a calculator, then I'm looking for that. Here's my base 3 raised to the log base 3. If that's true, then this is just going to equal 7, and the reason that's going to just equal 7 is because I'm using this rule right here. This is base e, and I see natural log, so that is base e. So b is just equal to 3.7. And again, I'm using this rule right here. I have base 5 raised to the log base 5. So this is just going to equal 7x plus 5 for this reason. I have base e of e. So I know this is just going to equal 5. And it's for this reason. And then I have the common log, base of 10 raised to the x plus 16. So this is just going to be x plus 16, and that's for this reason right there. So all of these are able to be simplified without a calculator by using just those two rules. If I'm asked to break this apart with the sums and differences and everything else, then I need to look to see what's going on between each one of my factors, if they're factors or if they are terms. And I know they're factors because I have multiplication going on between them. Because I have multiplication going on between them, I'm going to break this up with the product rule. So this will be the log base a of x cubed plus the log base a of y squared. Now I'm going to use the power rule, which means this power on the 3 is going to come down out front, and this power on the 2 is going to come down out front as a multiplier. So this is going to equal to 3, the log base a of x, plus 2, the log base a of y, and that's my final answer. On b, it is division going on between them, so I know I'm going to break it apart with the quotient rule. So this is going to be the log base b of x squared minus the log base b of y. This x has a power on it, so I'm going to bring that down in front as a multiplier by the power to power rule for logarithmic functions. So this is going to be 2, the log base b of x minus the log base b of y. My next example has, well, actually, look at that. My next couple of examples have way more going on with just those. So I'm going to break it apart step by step. I have the numerator, 5a, and I have the denominator, 4b. So I'm going to write this as the natural log of 5a minus the natural log of 4b. So that's my first step. Between 5 and a, that is multiplication. So I'm going to break that apart with the product rule. So this is going to be equal to the natural log of 5 plus the natural log of a minus. Now I put a parenthesis here because I know what's going on between 4 and b is multiplication. So it's going to be the natural log of 4 plus the natural log of b. And I'm breaking those apart with the product rule. And I can leave the answer like that. That's perfectly a legitimate answer. Or I can distribute the negative through. So I have the natural log of 5 plus the natural log of a minus the natural log of 4 minus the natural log of b. And that is a perfectly legitimate answer as well. On D, I have again a numerator and a denominator. So I'm going to break it apart in those two pieces first. So I have the common log, or just log, 10x squared minus, actually, let me do this. Let me do it with consistent colors. So my numerator, my denominator. So this is going to be equal to the log of 10x squared minus the log of y cubed z. Between 10 and x squared, it is multiplication, so I'm going to break that apart with the product rule. And between y cubed and z, I'm going to break that apart with a product rule. So this is going to be the log of 10 plus the log of x squared minus the log of y cubed minus the log of z. And what I did there is, because I know that I'm going to have to distribute the negative through, or I can distribute the negative 1 through, I'm going to go ahead and distribute the negative 1 through as I break it apart. That way I get used to whenever I see negatives, they're going to go in the denominator. So I have to deal with this exponent on the x and this exponent on the y, and I also know that that value is 1 because it is the log, it's a common log, which is log 10, so log base 10 of 10 is 1. So this is going to equal 1 plus 2, the log of x, minus 3, the log of y, minus the log of z. And that's my final answer. On E, it looks like it's really difficult, but what I'm going to do is I'm going to simplify what's inside the square root first, because it does have simplification there. So if I can simplify before I break apart, I do. All my previous examples, I didn't have any kind of cancellations or simplifications. I'm going to use the rules that I know for exponents, which is here, this is going to become just a to the 4, because I'm subtracting the exponents. This is just going to become b to the 3rd, because I'm just subtracting the exponents. It's underneath a square root, which is the same thing as a to the 4th, b to the 3rd, raised to the 1/2. I'm going to distribute the powers through, so this is going to be a to the 4. 4 times 1/2 is just 4 divided by 2. b to the 3 divided by 2. And so I end up with a squared b to the 3 over 2. So what this is equal to is the log based a of a squared b raised to the 3 over 2. Much simpler to work with. Now, what's going on between a and b is still multiplication, so I am going to break it apart with a product rule. So this is going to be equal to the log based a of a squared plus the log based a of b to the 3 over 2. Log based a of a to a power is just equal to that power, so this is going to be equal to 2 plus the log based a of b to the 3 over 2. Oh, but I could have taken care of that exponent at the same time, so let's take care of the exponent at the same time. So let's bring that exponent out front as a multiplier, so just 3 over 2. And that's my final answer. Now we're going to reverse this. So we have spent the time breaking them apart. Now I'm going to reverse this. And if I see addition, that means I am multiplying those two numbers, the 75 and the 2. So this becomes the log based a of 75 multiplied by 2. So in other words, the log based a of 150. Here I see subtraction. That means I am going to divide these two numbers. This becomes the log of 54 divided by 6, which is the log of just 9. On my next example, I have addition, I have subtraction, I have a power I have to deal with. Oh, and I have a lone number. We talked about how to deal with that lone number. So let's first deal with the power. That power in the front of the log of a is going to come back as an exponent. So this will be the log based a, or excuse me, the common log of a raised to the 1 over 3. And then minus the log of 2. Now this, from our previous examples, is we know that if we have the log base b of b to the x, this is just equal to x. So we're going to reverse this. This is equal to 3. So we're going to rewrite this as this 3 as the log of base 10 of 10 to the third. And that's how I'm going to bring that back in. So this is going to be plus the log of 10 to the third. So this is subtraction, so that 2 is going to go in the denominator when I bring it back together. This is an addition, so that 10 to the third is going to go in the numerator when I bring it back together. So this is going to be equal to the log of 10 to the third times a to the 1/3. These two get multiplied, and then it's going to be divided by my 2. Well, 10 to the third is just 1,000 divided by 2 is 500, so my final answer is the log of 500 a to the 1/3. All right, 2 more. So then we're going to go into the change of base. I'm going to distribute this 3 through, or I can wait and bring the x and y together. It's totally up to you. I'm kind of inclined to distribute the 3 through. So I have the natural log of 2x plus 3, the natural log of x, minus 3, the natural log of y, plus 1. And you're thinking, oh, that's right, we're going to bring that 1 back in. And the way we're going to bring that 1 back in is because we know the log base b of b to the x is equal to x. So if I see the natural log here, then the way I'm going to bring this back in is the natural log of e raised to the 1 is equal to 1. So that's how I'm going to bring that back in. So I'm going to bring these exponents onto the x and the y, because those multipliers of 3 are exponents. Every time I see a subtraction, it's going to go in the denominator. Every time I see addition, it's going to come in the numerator as multiplication. So this becomes the natural log of 2x. The next thing I'm going to multiply is x to the third, and then plus times e to the 1. The only thing that's going in the denominator is y to the third. So my final answer is the natural log of 2e x to the fourth all over y to the third. All right. So my last example here is, I know that each one of these multipliers are going to come back on as exponents. So let's go ahead and bring those back on as exponents. So I have the natural log of x squared minus 9 raised to the 3 over 2 plus the natural log, minus the natural log of x plus 3 raised to the 3 over 2 plus the natural log of x plus y. Now, when I see addition, I know that with addition, that's going to go in the numerator, and when I see subtraction, that's going to go in the denominator. So these two will get multiplied, and then it will be divided by this. This is going to be equal to the natural log of x squared minus 9 raised to the 3 over 2 multiplied by x plus y all over x plus 3 raised to the 3 over 2. And I'm not done. I'm done with what we've learned for logs, but I'm not done simplifying from what we learned from algebra. I know that x squared minus 9 is x minus 3 multiplied by x plus 3. So if I have x squared minus 9 raised to the 3 over 2, then that's going to raise these to the 3 over 2. But then by the power to power rule, this is going to be x minus 3 raised to the 3 over 2 multiplied by x plus 3 raised to the 3 over 2. So my numerator expands out, and I'm going to do this so that I can cancel with the denominator. So x minus 3 raised to the 3 over 2 multiplied by x plus 3 raised to the 3 over 2. multiplied by x plus y, all divided by x plus 3 raised to the 3 over 2. And again, I'm doing this so I can cancel those two terms out. So my final answer is the natural log of x minus 3 raised to the 3 over 2 multiplied by x plus y. And that's my final answer. That was a lot. All right. If I want to put in my calculator the log base 3 of 39, some of the new calculators do it, and you don't even have to do an expensive calculator to do the change of base, but most of them don't do it yet without doing some fancy smanciness. So we're going to learn something called the change of base. So if I have the log base b of m, then I can write the log base b, let me do this in a different color, log base b of m as the log of m as a log based a of m over the log based a of b. And you're thinking, why would I do that? Well, if I go back up to my example up here, if I'm trying to evaluate the log base 3 of 39, as long as my bases are the same, I can bust that apart with a change of base. And two bases that I have on my calculator are natural log and common log. So I can rewrite this as a log of 39 divided by the log of 3. So I can put those two in my calculator and get an answer. Or I can write this as a natural log of 39 divided by the natural log of 3. I want you all to put those in your calculator, and you should get the exact same answer, whichever way you go. So I can change the base on any of these using my change of base. So if I have the log base b of m, I can write it as the natural log or the common log or any other base that I need. So if I want to change my expression to the indicated base 10, then this is going to be equal to the log, the common log, of x minus 2 over the common log of 3. So on my next example, I have 3 raised to the x, and I want to change this to base e. So on b, to change this to base e, we're going to use this rule that says if we have e raised to the natural log of the natural log of some number, then that just equals some number. And that's going back to those ones that we did up here. Let me just scroll back up there. It's going to be way up here when we did, way up here, these. I'm going to use this rule right here, this one. And so I'm going to rewrite, and you'll see this on your homework, 3 to the x as e raised to the natural log of 3 raised to the x. And now I have a base e. On c, I'm going to convert this to base 6, which is going to be equal to just the log base 6 of 60 over the log base 6 of 9. Now you'll notice that on a and c, I approached them differently than I did b. The reason I approached it differently is because on b I had an exponential, so I had 3 raised to the x. Whereas a and c, they already were logs base 9 or base 3, and I was just asked to change it to the different base. But with b, I actually had to use e raised to the natural log of 3x to have a base e. And that's because it was an exponential to begin with and not logarithmic ones. My last 3 examples is I want you to use the change of base, and it doesn't matter if you use natural log or common log. I want you to use the change of base and evaluate these to 4 decimal places. I'm going to use, for this first one, I'm going to use the natural log. So I'm going to write this as the natural log of 12 over the natural log of 3. And in my calculator, I get approximately to 4 decimal places 2.2619. On e, I'm going to use the common log won't matter which one you use. I'm going to use the common log. So common log of 100 divided by the common log of 5. And in my calculator, to 4 decimal places, I get approximately equal to 2.8614. And then my last one, go back to the natural log, or I could use the common log, and I get the natural log of 60 over the natural log of 9. And in my calculator, I end up with 4 decimal places, 1.8634. Okay, so practice these, and the more practice you get, the better and more fluent you're going to get on these, and the more fluid and easier it's going to be when you do your homework and then when it comes to the test. Let me know if you have questions.